Okay, this is first unit. This is presented by M. Ravindra from Aditya College of Engineering. Is it clear? The audio is clear? Is it clear? Anyone
Yes,
response?
sir.
Okay. Okay, see the before going to the HVDC transmission systems, let us see about how power is transmitted through AC system. First, let's see. We have to know the basics of how the power is transmitted in AC system. Okay, see the figure. From the figure, we can observe that there are two generators. G1. Here we can observe G1 and another G2. Two generators. From one end, this is sending end. Suppose we consider this one as load end, or we can consider it as any infinite bus, load and bus, like this we can consider, or any whatever it may be. It is a motor or it is a generator. This G2 I'm saying, it may motor or a generator, anything, infinite bus or anything. Okay, suppose it may be generator, no problem, it is okay. Z1 and Z2 generators, how the power is transmitted, we have to see now. Okay, uh, here we are noted denote as P1 as power generated at G1. Similarly, at G2, P2. Okay, and here U1 is the voltage at the generator G1, and U2 is the U2 is voltage generated at G2. We noted like that. We can observe from that, and the transmission here also see transmission line reactance is there X here. The transmission line reactance, and between that means from generator 1 and generator 2, in between that one, some transmission line is there. The transmission line reactance is showed as X here. Okay, and now to calculate power transmitted to the transmission line, see at P1, how to calculate the power transmitted line P1. See that one, you P1 is U1 square by Z1 plus P, we considered here, and this P means P is equal to U1 by U2 by X sin theta. U1 means voltage, that is voltage generated at G1, the voltage that sending end voltage, and UT is the receiving end voltage by X, that is meant reactance, and sin theta is angle between the U1 and U2, that is voltage across the generator and voltage across the generator 2. Okay, V1 and this V1 and U2, angle between these two voltages. Okay, that is considered as theta. Here maximum power is transmitted across the transmission line when theta is equal to 90 degrees. When theta is equal to 90 degrees, we get maximum power transmitted from this G1 to some infinite bus, like here like this infinite bus. Okay, now what we have to know is here power transmitted depends upon the reactance values. P is equal to, see here, this is the power transmission, power that transmitted through the transmission line, P U1 U2 by X sin theta. Here X is variable and sin theta is variable here. See, maybe the distance increases, what happens? If distance increases, reactance also changes, X also changes, and as well as theta also changes. Increase of distances changes the angle here. Clearly you can observe here the angle is changed here, can be changed here. That means power transmitted depends upon the reactance values, and as well as this angle between V1 and V2, like that you can consider. And when, and that means that power transmitted depends upon the change of load angle and also change in the reactance. Okay, and that may be reactance, it may be XL, and the reactance, inductive reactance and capacitive reactance. Not only reactance, we have other parameters also. Resistance of the transmission line we have, and as well as conductance G. That is also, as here we know that resistance as R is directly proportional to rho L by A. Say, all of you mute your audio so that we can clearly talk. Mute your audio, please. Mute your audio. What we are saying here, there is, it also depends upon the parameters like resistance, inductance, capacitance, and as well as conductance. R is resistance is directly proportional to L by A. That means here, as the area of the cross sections of a conductor increases, what happens? Resistance value will be decreasing, right? Resistance value will decreases. That means what I am saying is, in a long transmission line, suppose if it is a transmission line is long, that what I am saying this one, the long transmission line, x by r ratio, and the reactance by resistance ratio is always high value. The x by r ratio will be very high value for long transmission lines, whereas for short transmission lines, that is distribution lines, when we consider for distribution lines, the x by r ratio will be very low. Okay, suppose here say, you can clearly observe, right, in a transmission lines, the distance between the two conductors, if you consider in a long transmission line, say two conductors distance will be very high, right or not? And also you can clearly observe in a distribution lines, the distance between the two transmission lines is also very low, due to the distance as high in high transmission lines. Suppose high transmission the distance is very high. Why the distance is very high in high transmission lines? Because we have to transmit a large power from one place to the other place. To transmit a large power to the other place, from one place to the other place, what is, we have to maintain the voltage levels at higher level, right or not? We have to maintain the voltage at higher levels. That means 220 kV, or we can say 132 kV. These are high voltage levels. When you are maintaining the voltages at high level, what happens here? Some inductive effect will be very more, will be high. Inductive effect between the two conductors will be very high, and you can clearly, when you can clearly observe, when you are below the transmission lines, long transmission, there will be high inductance. Inductive effect will be very high. In a closely rainy season, we can observe clearly the inductive effect also you can feel also. Some inductance also you can feel in naturally I'm saying. Okay, you can clearly observe. In case of distribution lines, the distance between the two transmission line is very less. And here also finally we can clearly observe, by the relation of R is directly proportional to rho L by A. Clearly area of the conductor of the size will be in distribution lines is very less, very low compared to that high transmission lines, whereas area of the cross section of the conductor in high transmission line is very high. As area of the cross section in high transmission is very high, what happens? The resistance will be very low, right? When resistance is very low, x by r becomes very high. X by r becomes very high, right? In high transmission, x by r will be high. That is the same case in case of distribution lines. They are very high. When we consider in distribution lines, x by r ratio will be very. Is it audible to all you? Hello? Is it audible?
Yes,
okay. Here x by, in distribution lines, x by r ratio will be very low. How we can say this one? As the conductor size compared to the transmission line, the conductor size of the distribution lines is very low. Yes, when area of the cross section area is very less, what happens? Area of the cross r, that r is directly proportional rho L by A, the distance will be very high. That means x by r ratio, when that is low, the x by r ratio will be high. Here finally we can say that x by r ratio is greater than 1 in case of transmission lines. X by r ratio is less than 1 in case of distribution lines. This is the main concept. You all have to know it. Wherever you go interviews, this is the question they ask. Fine. Definitely I'm saying. Okay, this is the main concept. You have to know, well, what is the x by r ratio, what is the x by ratio in the transmission lines, what is the x by r ratio in case of distribution lines, why it is high in case of transmission line, why it is low in case of distribution lines. This is the questions you all face in interviews. This is the that means we have to, that means ఇక్కడ మన ప్రాబ్లం ఏంటంటే, we're going for HVDC transmission system. We're going to study about HVDC transmissions. Now see here, the power transmitted from one end to the other end depends upon the line length, right or not? As line length increases, stability problems occurs. Finally, Okay, stability problems here, how we see here, and also stability problems that depends upon the phase angle stability, and also voltage uncontrollable voltage we have uncontrolled voltage here. It depends upon the reactance values, resistance values, conductance values, and parameters of all these transmission lines. It all depends in case of AC transmission system. For if you go for large power, if you go for large distance, if you want to transmit for large distances, these are the main problems in AC transmission systems. So now what we are going to do is, in case of DC transmission system, this is, it does not depend upon any reactance values, it does not depend upon these parameters all. So it is possible for DC transmission system to to send and so to send a large power to a long distance of to a long distances. See, what we do is, we place a DC link in between these two ends. We place some DC link in between these two links. Now let's see this one. See this one. Next slide, you can see here. This is the rectifier end, and this one is the inverter end. Okay, what we do is, this is the power generated, that AC is converted to DC here, and as well DC is converted to AC here. This is the long distance, whatever the long distance is there. In between, what we do is, we place the DC transmission system. DC links we call it as, simply what as DC links we call it as. Okay, here see the why we going for DC, there arise some technical problems of transmitting power to such long distance using AC. Though that why we put DC supply, DC links, and DC links are introduced. Okay, the first DC link was set up in 1954 in between Swedish mainland and the island of Gotland. The use of an HVDC link in AC system requires converter stations here at first end, converter station, that is rectifier station, and another end, inverter station. These two can act like reverse way. This can act as inverter station, this can act as a rectifier station, like this. Okay, it can be both. Like this rectifier station can act as inverter station, this inverter station can act also rectifier station. Coming to next slide. Okay, now what is the comparison between HVAC and HVDC? We already discussed now what it depends HVAC, what are the main problems in HVAC. Okay, how to transmit the power through AC, what are the main problems? The main problem is line length, uncontrolled power, over or low voltages during lightly or overload conditions, and we have, due to the phase angle stability problems we have, and fault isolation problems, all those. And here what we are advantage of HVDC is the ability to transmit large amount of power over long distances with lower capital costs and with lower losses in AC. Okay, and also this is also in case of, if we consider underground cables, where we use capacitances are here, due to the high capacitances in underground cables, there are very high losses in case of AC, so we can go for DC. Okay, what are the main criteria we consider in DC? Main criteria and compulsory requirements in case whatever, if you want to study AC or DC, if you want to study or AC or DC, three main criteria are required to be considered. First one is economic of transmission, technical performance, and third one is reliability. Wherever in every system, if you want to study any system, if you want to produce any system, these performances have to be studied compulsorily. Economics of transmission, technical performance, and reliability. Now if you go for economics of power transmission, now see this diagram here. Line of AC cost, line cost of AC, and line cost of DC we have drawn here like this. There is some intersecting point, see here, break even distance. Okay, this intersecting point of line cost of AC and cost of DC is called as break even distance. Okay, break even distance. And also we have mentioned here terminal cost DC, and terminal cost of AC. Here line cost of DC is very less compared to the line cost of AC. You can clearly observe from this diagram, right? And terminal cost of DC is very high compared to the terminal cost of AC. But when we compare to AC, here for long transmission of power, This is the best one. That means DC transmission is the better we consider. And also AC DC line requires 2 conductors, where AC line requires 3 conductors. Comparing 2 conductors, 3 conductors is very high, and production of cost of 3 conductors is also very high. The cost of the terminal equipment is very high, right? The cost of the terminal equipment is more in DC lines than AC lines. We have already discussed it. This point is considered as break-even. Is the intersecting point of line cost AC and line cost DC, where the cost is same for AC and DC. That is called as break-even distance. Okay. Next point, or coming to technical performance. So we have already discussed in first slide that when they going to technical performance, stability limits we consider here. Stability limits means what? The power angle. See, the power angle in case of AC depends upon the phase angle, right? The phase angle, the load, or we call it as the load angle. Load angle between sending end voltage and receiving end voltage. That depends upon the phase angle. Phase angle, and as line length increases, what happens? As line length increases, what happens means here there will be a deviation in, definitely the voltage deviation will be there. The power transfer capability also will be decreased. So okay, as distance increases, what happens is the power transfer also decreases. This is the main problem in we consider in main problem considered in stability limits. Clearly from the graph we can see here. In case of AC transmission line, see here, the distance increases. As the distance increases, power is going to decrease like this. In case of DC transmission, that it remains constant. Okay, the power carrying capability of an AC line is mostly proposed to transmit distance, whereas the power carrying ability of the DC line is unaffected by the distance of the transmission. Coming to voltage control. Okay, this we have discussed in this class very briefly about this also. Who may lost, who may are not there in the class, can listen now. Now see here. See, we have what is sending end voltage. This one, yes, from the diagram. How the voltage can be controlled here. See, in AC, what is the difference between AC and DC? Sending end voltage is equal to the V, certain voltage V, and here receiving end is equal to V. Okay, see here, and Vx is the some distance in case of that is load when P is less greater than Pn equal voltage. What is this Pn? What is Pn? We have to know what before to know the Pn. We have to know about SIL, surge impedance loading. Surge impedance loading. Surge impedance loading. How we consider the surge impedance loading? See here, this is the case where in a transmission line, suppose consider a transmission line having shunt inductance capacitive values. We have transmission having capacitive values and as well as inductive values, right? Okay, when the maximum power is transmitted, means the voltage is also certain level. Sending end voltage is also equal to receiving end voltage, right? When the maximum power is transmitted, means that the theta is angle equal to 90 degrees. Okay, that position, that is the resonance condition. XL is equal to XC. That means here capacitive VAR is equal to inductive VAR. Okay, we can call it as omega CL is equal to omega C. That can be seen here. A capacitive VAR is equal to inductive VAR. We can write VCR by XC is equal to I square XL. In this we can derive V by A is equal to square root of L by C, that is ZS. ZS is nothing, surge impedance. Here surge impedance loading. What is surge impedance loading then? This is the derivation in case of maximum power is transmitted. Okay, right? That is nothing but just surge impedance. This impedance is nothing but impedance of the transmission line. Okay, this ZS is equal to the resistive load. Suppose the load is purely resistive. Suppose at receiving end, when we consider that the receiving end, when we consider the receiving end, here the receiving end means we are here when the receiving end, in case of here the load is purely resistive. Okay, the resistive load, the resistance of that load is equal to the impedance of the transmission line. At that condition, that is what we call it as surge impedance loading. At that condition, P is equal to Pn. At that condition, what we call it as P, power transmitted, is equal to natural power. Okay, P is equal to P. That means here the maximum power is transmitted at this point. That is sending end voltage is equal to receiving end voltage. Here also sending end voltage is equal to receiving end voltage. Okay, did you understand this one? And when suppose this resistive load, the surge impedance is not equal to the resistive load, then P is greater than P. In this condition, the voltage will be very below, and in this condition, the voltage will be P is less than P, and the voltage will be very high. Okay, Finally, we can define here, so SIL is defined as power delivered by a line to a purely resistive load equal to the value to the surge impedance of that line. Okay, did you understand? Do you understand all this? Okay. Next, coming to line compensation. To compensate the line system, so is it audio visible, audio audible to all of you? Hello? Hello? Is it audio audible?
Yes, sir.
వినపడుతుందా? ఓకే ఓకే లెట్స్
Yes, sir.
ఓకే అర్థమవుతుందా మీ క్లాస్ వినపడుతుందా క్లియర్గా? హలో
అర్థమవుతుంది సార్.
ఓకే అమ్మా
వినపడుతుంది సార్.
okay. Let's so next slide is line compensation. What are the problems on line compensation? Line compensation is necessary for long distance AC transmission to work on the problems of line charging and stability limitation. To work on these all problems, what we do is we install SVC systems, static wear compensators, we call it as static compensators, statcoms. We are in between the midpoint of the transmission system or end point of the transmission system, or if required at the starting point of the transmission system. Okay, we are going to these all install these devices to compensate the reactive power. Somewhere the reactive power may be decreased, somewhere the reactive power may be high. To observe that one, inductive reactors are placed to send some mini reactive power, to generate some reactive, some condensers are placed. Okay, these are how line compensation is done. Next one is problems of interconnection. When in problems of interconnection means, we suppose two grids we have to interconnect. That means through tie lines, two power grids should be integrated. One is that means two grids, when we want to intersect two tie lines, what happens is we have to consider parameters of that one. Two parameters means there we have to consider frequency, impedance values. Those two values should be equal, compulsory. Okay, if you want to transmit the power by intersecting two power grids, those two are considered. When we are intersecting that problem, there will be large number of problems. The presence of large power oscillations which lead to the frequent tripping, increase of fault level, transmission of disturbance from one system to other. These are the main problems occur in case of intersectioning of two tie lines. Okay, next, these can be overcome by DC lines. When we place in case of AC lines, through DC lines, these problems can be eliminated. And also, suppose asynchronous interconnection means one grid may be operated one frequency, another grid may be operated in another frequency. These two can be integrated by DC links. In case of DC power system, these two can be integrated. Okay, next, coming to ground impedance. See here, ground impedance. Ground impedance means here, why you consider ground impedance means here, when DC pulses, in case of DC is, see clearly listen here, in case of DC systems, that is current is DC, not AC, DC, the current flowing will take the written path as ground. Clearly listen here, the current takes the written path as ground. Okay, only one conductor will be there and the current will be flowing through the ground. Here clearly ground impedance, see here, in the case of ground impedance, what we are considering here, the current will be flowing through the ground. Okay, two conductors will be there, one is ground, we consider only one conductor, we consider ground as if consider, and that means metallic return, we call it as a ground. Okay, the current will be passing through the ground here. In case of AC, that is the not case. That is the not case in case of AC. Here ground is high impedance. Ground have high impedance. Oh, here the written path takes through neutral point in case of AC, but in case of DC, it does not take through. In case of AC, it takes the written path through neutral, but not through ground. Okay, here the ground is high impedance. Is so the current cannot be flow through the ground here. These are the main problems. Okay, the current cannot be flow through the ground here. The ground impedance is negligible for DC currents, whereas in case of AC, it have high impedance, so the current cannot be. These are the main problems there. What are the problems we are correcting here is in AC transmission, the existence of ground current cannot be permitted in steady state due to high magnitude of ground impedance, which will not only affect efficient power transfer but also result in telephone interference. Here the problem is telephone interference. Telephone interference problems occurs due to the high impedance provided in the ground here. Okay. Next, reliability. Okay, here the next case is reliability. There are two measures of overall system reliability. Energy availability and transient reliability. Okay, these are the formulas to check the performance of the system. Whether if it is suppose one DC system you have proposed. Okay, to check the performance of the DC system you proposed, what we consider the main is energy availability and transient reliability. These are the formulas given here. Energy availability is equal to 100 minus 1 minus equivalent outage by actual time into 100 here. Okay, where transient reliability, this is the factor specifying the performance of HVDC system during recallable fault. When in case of any fault occurs, that how to check that one. Here, transient reliability is equal to 100 into number of times HVDC is performed as designed by number of recordable AC faults. This is how reliability is checked using these energy availability and transient reliability formulas. Okay. When we comparing the HVAC and HVDC transmission system, next slide here. Here see the diagram. We can clearly observe that one. See the peak voltage is high of in case of AC compared to that of DC. Here the peak voltage is high, right? Compared to DC value. See, this is the low compared to that of DC. So, as the peak values of the AC are very high, the losses of the current also will be very high. Okay, HVD uses less currents and low losses. In case of HVDC, we have less current and low losses. Now, in comparison of HVAC and HVDC, in case here the conductor, see only single conductor for DC, 3 conductors for AC. Therefore, here also HVAC 3 conductors, HVDC is only 1 conductor, and the cost of this HVDC is less compared to that of HVAC. And next, transmission towers we see consider. In case of transmission towers also, we use more number of transmission tower for in case of HVAC. We use only single tower for HVDC device. So the cost of the transmission towers also very less in case of DC compared to that of AC. See here, AC transmission line corridor. You can see here, okay, more number of transmission lines here. Due to this more number of transmission lines, there will be certainly corona effect. Here the corona effect will be is high in case of AC transmission line. As we have more number of transmission are gathered in a group here. See, more number of transmission lines are there. Corona effect also is high here. Here also see in DC transmission, here the distance from one tower and tower also is very long, and as well as here the transmission lines and only one transmission line is there. Here we see VAC, more number of transmission lines is there. Here more number of transmission are there. Here only one transmission is there. See, and here the corona effect is also very less in case of this one. Okay. Now see lesser corona loss than HVAC at some same voltage and conductor diameter and less radio interference. Direction of power flow can be changed very quickly. HVDC has greater reliability, that is bipolar DC is more reliable than 3 HVAC. We can discuss bipolar DC next one. DC requires less insulation here. Okay, in the same graph we have already discussed this one. Next, coming to components of HVDC systems. Now coming to components of HVDC system, we use converter unit, converter transformer. See the converter unit, this is all we consider as converter unit. Converter transformer, these are the converter transformers. Harmonic filters, here the place harmonic filters. See at the rectifier station and as well as inverter station, we place these harmonic filters. Reactive power supplies and compensation device, SVC device, STATCOM device, all those devices are can be placed for rectify to compensate the reactive power. Okay, electrodes to earthen the supply, to earthen this one we use electrodes. And DC lines are used here. AC circuit breakers and DC switchgear system are used to avoid the fault conditions in case of AC and as well as DC. Okay, next coming to converter unit. To briefly discuss about this converter unit. What will a converter unit does? First, it acts as a rectifier, convert AC to DC, and as well as inverter to convert DC to AC conversion. See here, we can observe these are two 6-pulse converters arranged in parallel. Here two 6-pulse converter here connected, and the converter is fed by the converter transformers. See, converter transformers is star to star, and star to delta connection arranged here like this. And how these converters are cooled by using water of freon or liquid cooling using deionized water is more efficient and results in reduction of station losses. By using this water of freon or deionized water, these walls can be cooled, okay, and maintaining the temperature required. Next, valve firing signals. How we give the signals to the this one thyristor devices through fiber optic light gate system. We give firing to trigger the thyristor devices. So we have to give the firing gate pulses. Those are given through fiber optic light gate system. Fiber optic light gate system. And how to protect this converter unit? How we protect through snubber circuits and gapless surge arresters. By using snubber circuits and gapless surge arresters, we can protect this converter unit. Next, coming to converter transformer unit. Now there is a three types we can see is configuration: 3-phase 2 winding, single phase 3 winding, and single phase 2 winding. See, these are connected in parallel with the neutral grounded here. Okay, and also the main point if we have to remember here is the leakage reactance of the transformer is chosen to limit the short circuit currents through any walls. This is the main point. That means here whatever the overlap occurs, and with overlap and without overlap, when we consider the cases, the leakage reactance plays a main role here. That have to be considered here. Okay, the converter transformers are designed to, and these the converter transformers are designed to withstand DC voltage stresses and eddy current losses due to harmonic currents. There may be harmonic currents injected from the rectifier side, or also inverter side, both sides. At this both sides we use transformers so that these are built in such a way that to withstand the voltage stresses, both eddy current losses due to harmonic currents, these should be minimized. Okay, next, components of HVDC transmission systems. Okay, that one, continuing that one. Okay, we have filters. We have where we place filters here at the rectifier station and as well as inverter stations. We have both AC filters and as well as DC filters. Okay, and also high frequency filters depending upon the frequency conditions, if any. Okay, and now AC filters, these are passive circuits used to provide low impedance path. When we consider AC filters, low impedance is provided always. If you see, I already told you in class that says that to any fault, suppose any fault occurs or any unwanted harmonics are there, if you provide a low impedance path to that one, what happens? The fault current or harmonics, whatever present in the system, those will be flowing to the ground through the low impedance path. It always takes low impedance path. Any current flowing or this one, how current will be taking always the low impedance path. Here what in AC filters they do is always provide the low impedance path depending upon the frequency conditions. If it is depending of the harmonic, third harmonic or seventh harmonic, depending upon that one, different filters are designed such that the harmonics are removed through the by providing the low impedance path. And similarly for DC filters, say in case of AC filters, what we do, in case the DC filters also, DC harmonics are also eliminated. Certain harmonics are eliminated by providing those low impedance paths. And also high frequency filters, these are connected between the converter transformer and the station AC bus to suppress any high frequency currents. Certain and that means here also for high frequency filters also, the impedance is built in such a way that that high frequency harmonics, whatever harmonics are there, that will be passed through that impedance values. Okay. Next, components of HVDC transmission systems. Smoothing reactors. Smoothing is mainly to smoothen the or remove the harmonic content in the device. Okay, harmonic content in the uh, rectifier devices. Okay, whatever the rectification, after rectification the harmonic content, suppose any harmonics are produced, those can be removed using the smoothing reactor devices. They decrease the harmonics in voltages and as well as currents in DC lines, and also prevent from commutation failures in inverters also. Okay, and also in next one is reactive power supplies. The smoothing reacts mean, what are the smoothing is mainly used for? To the smoothen, that means remove the harmonic content, whatever the present in the rectifiers as well as inverters, the remove the harmonic contents. Whatever unwanted currents that are put, distorted currents are produced, these will be removed by using the smoothing reactors. Next, reactive power supplies. Reactive power supplies means under transient condition, it could be much higher. This under transient condition, uh, under transient conditions, uh, hello, the reactive power consumed by the converter is about 50% of the active power transferred here. Okay, when in case of rectification, in case of inversion process, AC to DC conversion or DC to AC conversion, here the reactive power consumed is high. Okay, it is about 50% of the active power transfer. So so compulsory there should be some filters, there should be some filters or any compensating devices provided at the near to the rectification station and as well as inverter station. That means here the AC filters are provided like that. We here reactive power sources are provided here. And as well as at the inverter station also some reactive power sources are provided. And next, electrodes. See here some electrodes are conductors that provide connection to the earth for neutral. Here for neutral case, you see this one neutral case to provide uh, to pass through the earth. The current will be passing through the earth through the electrodes here. Okay, and the DC lines, whatever these lines are there, we call it as DC lines. DC lines are very similar to that of AC lines. Okay, and now AC circuit breakers. They use it to clear the faults in transformer and for taking the DC link out of service. Okay, any faults occurs in the transmission line systems, AC circuits will be operated such that, and AC part means before this one, so the rectification is there, this is all AC part. Okay, this AC part can be isolated using the AC circuit breakers. Okay, and next, DC faults are cleared by converter control. And you suppose if you want to clear the DC faults by rectification in a rectifier fire, by using firing pulses, by using gate pulses, whatever there, by giving some signals, we can control this. Some modulation techniques by control this rectification and inversion pulse can be controlled in the DC faults. And also some DC switch gears are there here to some in latest trends, DC breakers are produced, that is metallic return transfer breakers like such that to these can isolate only small current. That means if any high currents are produced, these also cannot be these breakers also cannot these can be damaged. Only in case of very small current, in small DC current, these devices can be used, such as DC breakers or metallic return or transfer breakers. Okay. Next, coming to HVDC configuration. HVDC links can be broadly classified into here monopolar links. I think everyone is in monopolar links, bipolar links, and homopolar links. You can clearly observe here only one conductor is there. Monopolar link means only one conductor is there here. You can observe from the diagram. See in diagram, only one conductor is there. Okay, it have return path. See this one. This is one conductor and have return path, metallic return paths. Okay, it may be a water also. Okay, a metallic may be used where earth is resistive is too high. That means suppose the ground impedance is always high, we know that. Okay, as ground impedance is very high, it cannot, the current cannot pass through this. So a metallic return is placed here such that current passes through the like this closed path. Okay, this configuration type is first step towards the bipolar link. Next, bipolar link, we have two conductors here. Each terminal has two converters of equal rated voltage connected in series on this side. Here see the junction between the converters is ground. Here see here, okay, this one converter, two converters here. And junction between the two converters here and here, junction between the two converters is grounded. Okay, junction between the two converters is grounded. Okay, if one pole is isolated due to the fault, other pole can be operate with ground and carry off the rated load. Suppose this one pole is this pole, this we all call it as one pole, this all we call it as one pole. If one pole is isolated, okay, other pole can be operated. Okay, next, homopolar links. Okay, see here, these are written here also, and one or two monopolars we call it as homopolars. It has two or more conductors all having same polarity, usually negative. The polarity is always negative in case of monopolar and as well as homopolar. Here the polarity is negative here. Okay, see, here under one if we call it as more than two monopolars, we call it as homopolars. Okay, here the written path is there, you can clearly observe here the written path is there. Okay, see, here we consider there is no written path in bipolar. There is no written path. Similar to this is similar to the monopolar. Okay, here we have written path, this is here we have written path similar to the monopolar. Okay, like this one, and that we called as one or two or more than two monopolars we called as homopolar links. Since the corona effect in DC transmission is less for negative polarity, polar link is usually operated with negative polarity. The written path for such system is through ground. Here is the ground. Okay, okay. A modern trends in DC transmission. Okay, coming to the last topic, this one. This is about modern trends in DC transmissions. The trends which are being introduced are for the effective development to reduce the cost of the converters and to improve the performance of the transmission system. Okay, power semiconductors and valves. If see here, now we are using so many devices. First, before mercury arc devices are used at the starting of the HVDC system, and later than thyristor devices, IGBT devices, GTOs, okay, and so on. We are going using present IGBTs and GTOs. But here, what is the main problem here is IGBTs or GT employed require huge amount of current to turn it on. This is the big problem here. Okay, GT these are available at 2500 volts and to 100 amperes. This is the and to turn it off is also very difficult because it requires high current. So especially another device is used to turn it off. The semiconductor, to turn it off the semiconductor device, we use another device, that is MCT device, that is mass controlled thyristor test, which can be switched off by a small current. This can be switched off by a small current. So instead of having 2100 amperes to switch off, it cost also increases. Cost also increases. The device is it is very difficult to turn it off at such a high current. That's the main problem here. So we use another device to switch it off, and by using a small current. Here MCT device is used here. And these power ratings of thyristors can be increased better cooling methods. That means we have discussed in the deionized water or cooling have new become standard and results are reducing. We have already discussed this one in the first slide before when we are discussing components of the thyristors. That is deionized is water is used to cooling for cooling purpose of the thyristor devices like that. Okay. Next, coming to converter control. Converter control. How do we convert the control device, thyristor devices, gate pulses, how you get different. Now the more number of methods are, and the main research is here on converter controls. Here converter, how to control the main problem also is here also converter control. Here converter, different techniques are there here for controlling the HVDC systems. Different techniques. In research, main research is occurring also this converter. Different methods, different control techniques. That means some algorithms are used. Some computer-based algorithms are used here to control the thyristor devices. Okay, may control the devices like PWM, pulse width modulation techniques, multi-level inverters, multi-level converters, so many techniques. So many techniques are used here, computer-based methods to control the converter devices. Next, DC breakers. DC breakers, and also here DC breakers is the main problem. Shut down the current to uh, at high currents is very difficult point. uh, Breakers, okay, to isolate the any system at high currents. That means this is a high power transmission, right? That current values will be very high, and when the current value is very high, to switch off the device, to switch off the system, it is very difficult, right? DC breakers, it is very difficult. So and research also is being carrying out here to find out new DC breakers, such that at any cost to shut down the power, or we can isolate the power currents, high currents. Conversion of, next point is conversion of existing AC lines. There are some operational problems due to electromagnetic induction from AC, right? We have already discussed in first slide that induction problems are there, electromagnetic induction problems are there for transmission of AC power to long distance. Okay, where an experimental project of converting single circuit of a double circuit is under process. Here what is existing of AC lines? The conversion of, and that means in AC lines, you are using three transmission lines, right? Three lines we are using, three conductors are we using. Oh, when we are using three transmission lines, oh, what here research is carrying out on convert that single line to the DC line. Okay, for every single line, we have three lines already designed and constructed. Already we are in process transmitting the power, right? The main thing is here, what the government want to do is they want to utilize these things to convert into the DC, utilize these what are there already there, okay, to convert into AC. We have three already in progress, three transmission lines are progress. Okay, they want to convert that AC into DC. That is conversion of existing AC lines operating with weak AC systems. Here this is the formula. Yes, here formula called as short circuit ratio. What this short circuit ratio does here? The strength of what operation with weak AC, the strength of the AC systems connected to the terminals of the DC is measured, measured by short circuit ratio. And that means here to find out the strength of the AC system means generator is connected to the rectifier. Rectifier before the rectification of the process. We are going and that means we have whether we have to provide the reactive power compensation, or if we want or not, it is necessary or it is not necessary. Then how to know that one? That can be known by this short circuit ratio, which is defined as short circuit level at the converter bus by rated DC power. If SCR is less than 3, the AC system is said to be weak. Okay, suppose this is the ratio here. If this ratio is less than 3, the AC system is said to be weak. Okay, the conventional constant extinction angle control may not be suitable for weak AC systems. Okay, this is the first unit. Okay, this is the first unit today. Okay, thank you all of you.
నోట్స్ క్వశ్చన్స్ అది
ఏటమ్మా ఇది చేస్తాను స్లైడ్ అయినా
పీపీటీ సార్.
పీపీటీ షేర్ చేస్తాను
ఎస్ సార్. ఓకే సార్.
ఓకే థ్యాంక్ యూ అమ్మా.